Hey everyone, my name is Kevin from the University of Maryland. I just wanted to thank all of the FOCI organizers for making this event possible, despite everything going on. Now today, I'm going to be talking about a new form of censorship we discovered recently in Iran. Now Iran has already had a highly sophisticated censorship system. We have a user in Iran trying to make a forbidden request. The censor has already had the capacity to censor multiple different protocols, DNS, HTTP, HTTPS. It can do so with deep packet inspection for keywords, host names, etc. It can inject dummy responses or black hole traffic, and it applies basically to all destinations leaving Iran. Now, outside the scope of this paper in the past, we had developed a tool called Geneva that automatically discovers ways to evade network censorship. And while running experiments in February this past year, we noticed something strange. We noticed that evasion strategies that had worked not 1 to 2 weeks prior no longer worked. We started seeing strange behavior coming from the censor. So specifically, instead of getting censored after we sent keywords, we started noticing censorship happening before we had even sent keywords. Instead of getting dummy responses from the censor, we just started seeing a lot of packet drops. And really confusing this, instead of this happening to all of our vantage points with uniformity, we're only seeing this happen to some destinations. After looking into this more and running experiments, what we determined is that Iran has actually deployed a second censorship system, which is used in conjunction with the standard censorship. And we've been calling this a protocol filter. Now, at a high level, the protocol filter matches connections it sees leaving Iran to protocol fingerprints. And any connections that it does not recognize, it just drops. Now, this only applies to some destinations. And altogether, this creates censorship in depth in Iran. Now in this talk, I'm going to discuss how the protocol filter works, how it fingerprints connections, how it censors connections, and just other mechanics of how it works under the hood. In the second half, I'm going to discuss ways that it can be defeated, and specifically packet manipulation strategies we discovered that work from either the client or the server side using our tool Geneva. So first, let's talk about how the protocol filter fingerprints connections. The protocol filter performs deep packet inspection on packets leaving Iran. The filter only monitors TCP. UDP packets, they're not monitored by the filter. The filter only allows 3 protocols, DNS, HTTP, and HTTPS. And the filter is only active on ports 53, 80, and 443. And these are the ports commonly associated with these protocols. What this means is that you can use any other protocol you wish on other ports. These are the only ports that, as of today, as of time of this presentation, the protocol filter is monitoring. Now, I'll note that the protocol filter does not actually associate each of ththese protocols to its corresponding ports. You can use any of these protocols on any of these ports, but no other protocols besides these 3 can be used on these ports. So let's look more at these fingerprints and what these look like. Now, in the paper, we actually reverse engineer the precise fingerprint that the protocol filter matches for each of these protocols. I unfortunately don't have time to discuss all of them today, so let's just look at DNS. So the DNS fingerprint has 5 requirements for packets in order for it to match the fingerprint. The first requirement is that the TCP payload of the packet must be at least 12 bytes long. After this, there are some qualifications about the structure of DNS itself. The query response field must be set to 0, the question count must be less than 15, and the answer count must be 0. And finally, just generically, it must have a valid DNS over UDP header structure. And violating any of these requirements effectively immediately results in censorship from the protocol filter. Now I'm going to talk a little bit more about this last bullet now because it's not a typo. You actually truly must have a valid DNS over UDP header. But recall that the filter is only actually active over TCP connections. So it only will ever see DNS over TCP packets. Now, the problem with this is that the structure of DNS actually changes when it's used over TCP. And the way it does that is there's an addition of a length field at the front of the header. As a consequence, normal DNS over TCP packets actually violate the fingerprint for DNS. The Iranian DNS fingerprinter is incapable of matching valid DNS over TCP packets. Now, this seems crazy, and the reason this hasn't actually caused a significant issue in Iran is specific to how the protocol filter censors connections, and I'll talk about that more in a minute. This is just one example of issues we discovered in the protocol fingerprints. We discovered some issue with basically all of them, and the details for each of these are in the paper. So now that we've established how it fingerprints, the next question is, how does it censor? So the filter drops all packets from the client. And here we have the client about to make a request over a forbidden protocol over a monitored port. The protocol filter monitors this request, and it will recognize that it's not allowed, but it does not drop it yet. It does deep packet inspection, sees that it's not okay, but it doesn't drop it. The packet actually gets through. What it does is it drops all packets from the client after the first non-matching packet. So the second packet, after it's been triggered, data carrying, if it does not match, it will now get dropped. And we believe this is the case so the filter can be more tolerant to packet reordering. It allows either of the first two packets it sees to match the fingerprint. This is actually why DNS over TCP doesn't seem broken in Iran right now, because there's typically no second data carrying packet from the client. The filter is not bidirectional, unlike Iran's regular censorship system. So the response from the server is unaffected. It only monitors packets leaving Iran and only affects packets leaving Iran. What this means is even after the protocol filter has been triggered, the server is still free to send packets to the client basically unimpeded. The client will just be unable to acknowledge or send any data back to the server. As a consequence of this new censorship system actually requires vantage points inside of Iran to study. And this is a pretty significant limitation to researchers. You can no longer probe it from outside the country and see this behavior. Now, there are more details in the paper about the mechanics of how the protocol filter works. We discussed the full fingerprints to each of these connections. We performed some brief experiments with who the protocol filter censors, since it doesn't affect all destinations equally. We study how many packets the sensor monitors. We find it just looks at the first two data carrying packets, and how long it remembers an offending flow. It's about 60 seconds, but that timer resets with every packet in the flow. So next, I'm going to talk about how the filter can be defeated. So in order to do this, we applied a tool we had built in the past, Geneva. Now, Geneva is a genetic algorithm. It discovers ways to manipulate packets such that it defeats censorship. These are specifically ways either the client or the censor can change its packet stream such that the censor is unable to censor the connection without harming the original connection itself. So Geneva strategies apply just from one side of the connection. If you want to learn more, I encourage you to check out our website. I'll link to it at the end, or the citation is in this slide. So we wrote a fitness function for Geneva such that it could run against and create new censorship evasion strategies for the protocol filter. And I'm going to talk about those now. So the first one Geneva discovered was injecting an innocuous fingerprint. So here's again our client about to make an outbound forbidden request. Geneva is going to catch that packet, and it'll make two of them out of it. And to the first one, what it does is it sticks a load on there to create a benign HTTP request. So get request for example.com, for example. But specifically, it breaks the checksum of this packet. So when this gets sent, the protocol filter will see this, and it will see that it matches the fingerprint. So once we've gotten approval for the protocol filter, it will green light the rest of the flow. Now, because this is a broken checksum, when it gets to the server simply drops the packet. Now, at this point, the client is free to communicate with its original protocol. The protocol filter already thinks things are okay, so it stopped checking fingerprints, and the server already dropped the packet for this strategy. Now, we actually found 3 such strategies that work from the client, and I'll talk about each of these. So the first is this innocuous request, where you just send some innocuous request with a broken checksum after the three-way handshake. This doesn't actually have to be HTTP. This works with DNS or HTTPS as well. The second strategy we found is a little stranger. It seems odd that it works, but before the client does its three-way handshake, it sends 2 fin packets. And this is sufficient to make the protocol filter ignore the rest of the connection. Now, the last strategy we found is likely the strangest, in my opinion. While the client is completing the three-way handshake, instead of sending 1 ACK packet, instead it sends 9 of them. And this alone is sufficient to make the whitelister ignore the rest of the connection. Now, we hypothesize this works because there's some internal limit on the number of packets the whitelister will process. But all of these work with 100% reliability across all of our vantage points. Now, next, I'm going to talk about server-side evasion. So instead of deploying Geneva at the client, we instead deployed it at the server. And this allows us to subvert the protocol filter from outside of Iran without requiring any client-side modifications. We actually found a strategy that works for this. So during the three-way handshake, what the server does is it sends 9 SYNAC packets with incorrect acknowledgement numbers before sending the original one. The effect this has on the client is it induces the client to send 9 resets. These 9 resets is now enough to push the connection, push the number of packets the protocol filter has to process over the limit. And just like that, the protocol filter will ignore the rest of the connection. So in total, here are the 4 strategies we identified to defeat the whitelister, the protocol filter, and all of these are in our paper. So that's just about all the time I have today for this talk. I look forward to discussing this more with all of you at the conference. Thank you.